Okay, so we've learned the 68, 95, 99.7 rule, and we know that if our data is normal, it must approximately follow this, where we have a mean here, we have a mean minus 1s, mean minus 2s, and mean minus 3s, mean plus s, mean plus 2s, s being standard deviation, and finally mean plus 3s. And this allows us to, find there was 68% of my data here. 95 leaves me with, I think it's 13.5% in each of these spots. And sometimes you'll just think of this outside edge as there's 2.5, there's 5% outside of two standard deviations. That's 2.5% on each side. Yes, this is really 2.35% and 0.15%. But this allowed us to find, okay, one standard deviation. What percentile is it? Well, it happens to be that all adds up to 16%, so it's 84th percentile. And that works great on the standard deviations. But what if I want something here? Or what if I want to know what the 80th percentile is? So we have a way of doing what we call standardizing. The standardized value, known as the z-score, it takes my value, it subtracts the mean, and divides by the standard deviation. You'll sometimes see it written like this. For true standard deviation, we must actually negate this. This is population mean. If you're going to use a true z-score, you have to know the population mean. So that's the population. That's everybody. It's the mean of everybody. In reality, most of the time we only have the sample mean. If we know the population mean, there's no point in sampling. Sigma is the population standard deviation. I'm going to abbreviate standard deviation with SD. And this is the sample standard deviation is S. So the z-score basically just scales everything so that we get a new normal curve with the mean at 0, one standard deviation above being 1, one below being -1. So you get these nice whole numbers. And that is the beautiful thing about z-scores. So now let's start applying them. So standardizing women's heights. The height of young women is approximately, and this is pretty accurate data, mu is 64.5, sigma is 2.5. That's pretty good. So if we want to know a woman's standardized height, 68 inches tall, that's 5'8". What's her z-score? 68 minus 64.5 over 2.5. Okay? That gives me, when you add it all up and do it, it's 1.4. You're looking for one that's 5 feet, 60 inches. You get a z-score of -1.8. Okay, so now let's make it useful. And we'll do this both with the calculator and with what's called a standard normal table or a z-table. There's a z-table right in the front of the book. I will post the AP formula packet that also has a Z table in it. It's got several tables. It's called Table A in that. So now we want to find the proportion of observations that are less than 1.4. So we just calculated our 68 to be 1.4. The standard normal table always gives you left or the percentile. So 1.4, if we go look at our standard normal table, and I'm going to explain how to use this. Okay. So here's a standard normal table. Well, this is all so far, this is negatives. I'm looking at this column right here. They're all negative, so we have to go to the next page. There's 2 pages. This is the positives. So I'm looking at 1.4 or 1.40. So I go look at the 1.4. This spot here is 1.40. 1.45 would be go in the 1.4 would be that. But what I get here is 0.9192. So my 5'8" girl is roughly 91.92 percentile, or approximately 92nd percentile for height. My 5-foot girl, negative 1.8. Now I need to go to the negative part of the table. It's also negative 1.80, 0.0359. So approximately 3.6 percentile. Maybe instead of a percent sign, I should say percentile. Okay, and my z-score ever so nicely gave me that. Okay, let's show you how to get this on the calculator. Menu, statistics. Wait, no. Menu statistics, distributions. This is considered a normal CDF. Z-score is normal CDF. Lower bound, it gives you upper bound. Let's do negative 1.8. 0.3593. Let's do the same thing again. Menu. You can actually go to the probability. Distributions is under there too. Statistics or probability. Distributions. Normal CDF. Let's do our 1.4. 0.9192. Now, if you want to be really fancy, probably doesn't matter. I said mine was 68 inches. If I change my mean to not be the standardized values and my standard deviation, so mean, remember that I calculated here, and you do need to be able to show this, but your calculator can do this for you. So I just changed my mu and my sigma here, and I entered my x. And it'll do it all for me. Same thing. So we've now been able to classify a percentile for a person's height. So now find the proportion of observations from the standard normal distribution that are greater than negative 2.15. So this is just the standard normal distribution, that's the standard normal table. So I find negative 2.15. I go to my negative 2.1 line, go over to my 0.05 column, and I've got 0.0158. It said greater. So what it's really looking for is this side. Remember, the standard normal table always gives me the left side. So to get the right side, I know that the area under my density curve is always 1. 9842. Essentially 98.42. A way that they like to see this drawn, and then the highlighted portion. Sketching them like that can be very helpful to keep track of what did it ask you for, especially if you have to do several calculations before you actually get to the table. Okay, using this again. What proportion of young women are less than 68 inches tall? Well, we already did that, and we get 9.9192. So, steps to finding it. State the problems in terms of variable x, draw and shade the distribution curve. Standardize, that's use the z formula. Find the required area using the standard normal table. Keep in mind if you have the upper side, you need to do 1 minus. And then finally, this is a new step that you need to start doing. Write your conclusion in the context of the problem. Don't just give me a number. Give me a meaning. Okay? That is something IB will be looking for. It is something college professors will be looking for. Don't just give a math answer, give me a meaning. So, this example, is cholesterol a problem for young boys? The level of cholesterol in blood is important because high cholesterol levels may increase the risk of heart disease. The distribution of blood cholesterol levels in large populations of people of the same age and sex is roughly normal. For 14-year-old boys, mu is 170 milligrams cholesterol per deciliter of blood, and the standard deviation is 30 milligrams per deciliter cubed. Okay, or per deciliter. I guess deciliter would be a cubic unit. Levels about above 240 may require medical attention. What percentage of 14-year-old boys have levels above? So state the problem. We're trying to figure out what percent of boys have bad cholesterol levels. We know that X has a normal distribution. Again, that's abbreviated N, mean 170, standard deviation 30. Sketch the distribution. We are looking for this part. Next part, we're going to calculate Z over 30, and that's going to be 2.33. Yeah, I'm right on that. So that's step 2. We're looking for Z greater than. Step 3, go to our standard normal table. Or use the calculator, but I like the table. And I need you to learn how to use it. 2.33.9901. Is that the side we want? No, we know we want we want the high side. So we need to go 1 minus 0.9901, and that is 0.01, 0.0099. So less than 1% of boys 14 have this problem. So my final step, write the conclusion. Only about 1% of boys have high cholesterol. Slightly less, but this needs to be said. You don't write that, you stop at step 3. You did not answer the question. You do not get it right. I will give partial credit, but you did not get it right. Okay, working with an interval. What percent of 14-year-old boys have blood between there? Well, 170, this is pretty easy. Because I just did this, 170 was the mean. Out here, I have approximately 1%. Well, above the mean is 50%, so this is 49%. So I finally stated in the context of the problem, 49% of boys have cholesterol between 170 and 240 milligrams per deciliter. Notice how I gave the units too, and just ignore those. Okay, now going the other way. So this is the standard normal score for SAT verbal. This was a lot of years ago, but N505 110, meaning mean of 505, standard deviation of 110. How high must a student score to score in the top 10%? Scoring in the top 10% would be greater than 90th percentile. So I am looking for what score is needed to score with an area of zero point 0.9 to the left. So I go to my standard normal table. I'm looking through my table to find where does 90% happen. So 0.8997 is much closer than 0.9015. So that is 1.28. That's my Z. Now I'm going to work backwards. This is my step 3. I've got my sketch. Point 0.9 is this area. So I don't know what my score is. I don't have a calculator handy, so I multiply by 110 and then add 505. And if I look at the book, it'll tell me what that works out to be. 645.8. So a student, finally, step 4. A student must score at least 646 to be in the top 10%. Okay, to be in, so it says in the top 10%, you must round that up. We must give that in interpretation of the problem. So I should say a student must score at least 646 on their SAT verbal to be in the top 10% of the SAT verbal section. I don't think they call it verbal anymore, but that's what they used to call it. Assessing normality. Method 1, construct a frequency histogram and see what fits where. So, the histogram in figure 2.2, page 78 of 947 Gary, Indiana vocabulary scores is close to normal. To assess it, we've effectively put these boundaries. So here's 3 standard deviations below the mean. Here's my mean. What I'm going to do is check, is this roughly 68%? So I take these together, I get 649 out of 947. That's 68.5. That's pretty good. Is this 95%? I add those numbers up, I get 903 out of 947. 95.4, that's pretty good. This should be 99.7. There's really only 2 that are not in there, so 945 out of 9 is 99.8. Yeah, this data fits pretty darn well. So what I did was and this would be tedious if you had to actually do it, but you have to, you know, take and tally mark everything until put it in each category. Figure out how many are in there, how many are in here. If you're doing a problem from the book, they're going to give you that kind of information. But we did need to compute, add those parts up to get the 649, get the percentage. Add everything up to get the 903, the 129 plus 331 plus 318 plus 125. All adds up to be 903 divided by 947, and you get 95.4. Compute the 945. Okay, that's method one. That one's pretty tedious, especially if you don't have the counts. Method two is what's called construct a normal probability plot. And to do a normal probability plot, I'll show you how to do that on the calculator. To do it by hand, you end up finding the distance away, and you're looking for it to be roughly linear. They're always going to be going up as they go across. This is pretty linear for small data. If it's not linear, it's not very normal. So let's look at the data. What data do they choose for me to use? We can't do that. I don't have that programmed. Let's see what I have saved in the calculator. Here, let's do Hank Aaron's home run data, because I have that data in here. So I'm going to add a data and statistics page. And I'm going to put Hank Aaron on this. And I get that. Menu, plot type, normal probability plot. This is relatively linear. Hank Aaron's data is approximately normal. It's not super good. But it worked. It's, somewhat normal, which is often all we'll need. So I did that again by plot type. I just put it on Hank Aaron on the x-axis, did plot type, and then that was normal. I selected normal probability plot. I could go back to my dot plot, which is the default. I could go to a box plot or a histogram, but we'll go back to the normal probability plot. Again, the more linear the data it is, the closer these fall to this line, the more normal it is. This one is sorta, but sorta is often ends up being good enough. And that's the end of 2.2. That's 2.2 standard normal calculations.